Hi, this is Terry Kushma here at Penn State University. What we're going to do today is look at further applications of carbon allotropes in part three in our series. So as we've been doing before, we're taking a look at briefly the history of the accreditation for different types of carbon allotropes that were researched. And currently we're looking at the area in the 1990s when the greatest credit went to a Japanese researcher for carbon nanotubes. So we're going to take a look at the discovery, the material properties of physics, manufacturing methods, and applications. So in 1991, Sumio Ijima discovered multi-walled nanotubes, or he's credited for it. This has been taken as a worldwide revelation, and this has led to development of other nanotubes and applications around the world. This has been, though, like in many of these applications, it was previously reported in 1952 by Soviet researchers, and they showed these and documented in the journals these particular units, but they really weren't respected at the time, and nobody knew what their applications were. In fact, I also think that in the same time period, they had the similar publications from the phone company here in the United States, AT&T, their research division in New Jersey. So they showed these fibers on the side and documented those, but nobody knew what to use them for. So carbon nanotubes, they were observed over the years, but not really seriously examined until 1991, when Sumio Ijima was working in NEC in Tokyo. Carbon nanotubes are highly ordered sheets of carbon atoms rolled into a tube. The carbon nanotube is a subset of the fullerene family, and it comes in two basic forms, the single-wall nanotube and the multi-wall nanotubes. And the diameters could be as small as 1 nanometer. So this gives us a view at some different types of nanotubes and their configurations that we can take a look at. And I actually think the one in the lower right is quite interesting, because what that shows is it's like a hybrid, that it has a fullerene coupled to the tube itself. And many of these things, when they're manufactured, these carbon derivatives, there's a very big Gaussian distribution of different systems that are made by that particular manufacturing method. So I think what this goes to show us is that the filtration is really important after we select any manufacturing method. The next step would be to purify this manufacturing method to get the media that we intended to use. So let's take a look at some material properties in physics. Nanotubes consist of carbon atoms covalently bonded in a repeating hexagonal pattern. This is a highly ordered pattern, gives the nanotube exceptional mechanical flexibility and strength. A perfect nanotube is 50 times stronger than steel at about 1/6 of the weight. So the large surface area on which it can be used to form bonds and to dope the nanowires or nanorods. The single-wall nanotubes have diameters from 1 to 10 nanometers. Multi-wall nanotubes can have many layers of tubes with an overall diameter of up to probably 20 nanometers. Thermal conductance is certainly high as diamond, and gases and other molecules can be stored in a cylindrical structure, and we discussed that earlier for fullerenes. So this is what a multi-layered nanotube looks like. So we can look at these geometries as H is the top portion, V is the sidewall portions, and C is the number of layers. And again, this is from Sumio, then Japan in 1991. So this shows the properties of the multi-wall, single-wall nanotubes, and when they're actually incorporated into epoxies as a composite. So basically what they're doing is they're taking these two materials together, the epoxy and the nanotubes, and they're making something that's stronger than either individual with more positive attributes. So this is a large use of these multi-walled nanotubes, because what they're able to do is for tension and mechanical applications, this distributes the energy across a physical material. So for example, if we had a carbon fiber arrow used for archery, it would actually exhibit a lot of strength and greater strength than steel across where the perpendicular to the nano wires themselves, or the nano composite itself. But on the other direction, it's not cross-linked quite well, because all the mechanical durability is in one direction. That's what these carbon nanotubes are able to do, is they're randomly associated within that matrix, and what they're able to do is mechanically support the object better. So this looks at the mechanical multi-wall carbon nanotube mechanical strength, and it shows that these things are add certainly to the strength of these epoxy composites, not only in one direction but on multiple directions. And this shows the different types of multi-wall nanoparticles and what they look like on the interior and the exterior. So now, excuse me, we're going to look at manufacturing methods. So there's catalytic vapor deposition. This is a VLS application, and we could use nickel, copper, aluminum catalyst to grow our nanowire. So what we're able to do, our nanotube, what we're able to do is selectively do our deposition on the catalyst and not the surrounding area. So basically, we would go through and run this application and wind up with nanowires preferentially grown where the catalyst existed. So one of the quintessential catalysts for carbon derivatives for nanowires, nanotubes, etc., is iron. So iron nanoparticles are deposited on porous silica substrate. The catalyzed iron nanoparticles are heated in a tube furnace. The hydrocarbon gases float over the pores in the substrate. The nanotubes will grow preferentially on the iron catalyst because they have a high accommodation coefficient for the saturation of iron. The tube shape and growth is controlled by the pore. So the pore is acting as a template to control the size of the multi-walled nanotube. This can grow both multi-walled nanotubes and single-walled nanotubes, and these are grown in a temperature of about 800 to 1400 degrees C. And these are grown in ambients such as acetylene in the range of 600 to 800 degrees C. And this is an example of carbon nanotubes grown from methane gas with iron nanoparticles as a catalyst. So as I said before, if somebody said, what's the quintessential catalyst for nanowire growth for carbon, I would say that it is iron. So there's also the high pressure carbon monoxide process. It's a relatively new process for producing single wall nanotubes. Carbon monoxide is a source gas. Catalytic iron particles are heated in a HIP-CO reactor at 1200 degrees. This process uses a higher pressure to facilitate growth in tens of torr. Many of the process methods can produce a single wall nanotubes, but they are selected to provide the highest yield for a particular nanowire. So we can also grow carbon nanotubes in a catalyst existing of molybdenum, iron, and copper alloy. And this can be deposited via sol gel on a porous substrate and then heated in a furnace to anneal them to the substrate. Then a hydrocarbon gas is flowed over the pores of the substrate to nucleate on the catalyst. The nanotube growth occurs at the site of the catalyst. We get both the base growth and the tip growth could be possible in this method. Of course, we would like to have all the time tip growth, not the widening around the base. CVD can grow both multi-wall and single-wall nanotubes, and they can grow from hydrocarbon gas feeds from a range from 8 to 1400 degrees, and multi-wall nanotubes grow preferentially more often when we have the gas feeds at a reduced temperature range of 600 to 800 degrees. So it's typical to control the distribution of different types of nanotubes or nano material that's grown in these processes by changing the pressure and or the temperature. And then at that particular mode, we'll get more of one type of material than the other. But I think it's important to note that we usually get multiple carbon derivatives grown in any of these processes. So again, filtration becomes necessary. So this shows us a schematic of the growth of carbon nanotubes with the catalyst. And again, what we're doing here is we're preferentially depositing a catalyst over a local substrate. What the substrate is going to do is provide a template to grow the chirality on the tube itself. And so what will happen is when the fluorocarbon gas is flown across the surface at a high temperature, what it will locally do is go into the catalyst area, supersaturate the catalyst. Once the catalyst is supersaturated, it has no choice but to try to minimize its energy. How it's going to do this is it's going to nucleate that particular gas alloy on the surface, such as the carbon. So the carbon will form bonds to the surface, allowing this system to minimize its energy. After it does that, of course, it's going to supersaturate again from the inflowing carbon gas to further make a nanowire. So carbon nanotubes can be synthesized in this recipe too, as you can see, and you're free to look at that chemical physics letter listed below. So again, what we can do, which is common to most of these processes, we can also go back and look at our arc discharge method as we did in other processes. Again, what we're trying to do is control the either the pressure and or the energy in this arc to get a tighter Gaussian distribution of a particular carbon derivative, but we get all of them in this particular method. So again, this is a universal method. I think it points out that these materials are rather difficult to do, and we get a multitude of different derivatives for any process, so filtration becomes really important at that point. So this shows us arc discharge method and some materials that were created from here. So it shows us these particular diameters, and you can look at that link down below in that particular research paper. So applications of multi-wall nanotubes, they're often used as fiber derivatives. So they're highly ductile and then also strong. So this is a chart here in a paper that shows the different types of multi-wall carbon nanotube type of fibers that could be used in manufacturing. So this gives us the different derivatives and compares their specific strength to one another. We can also look at LPCVD growth of carbon nanotubes to attain different nanotubes on the surface here. So this shows us the different diameters and the spacing. And again, you're free to reference that paper. So what I'd like to do is conclude our quick discussion of the multi-wall carbon nanotubes at that point, and we're going to go on with our next lecture and look at diamond nanowires. Thanks for your attention. We'll see you next time.